Hello friends, I welcome you in lecture number 5 on two-dimensional random variables. In this lecture, we are going to define certain terms related to two-dimensional random variables, which is nothing but generalization from one-dimensional random variables. So first definition is joint cumulative distribution function. So if we recall that if x is one-dimensional random variable from sample space to set of all real numbers, then if small px is probability mass function of this random variable x, then cumulative distribution function or distribution function is denoted by capital F and is defined as f of a equal to probability of the event x is less than or equal to a. That means we have to sum these probabilities starting from least value of x to this value. So probability, suppose starting value is 0, then we have to add up to this probability that x equal to a. Now similarly we can generalize this concept to two-dimensional random variable. Suppose we have two-dimensional random variable which is a function from sample space to R2, and suppose we consider two discrete random variables x and y, then xy is two-dimensional random variable. So cumulative distribution function of this random variable is defined in similar way. If we have one-dimensional random variable, we consider probability of the event x is less than or equal to a. Here we have two-dimensional random variable, so we will consider probability of the event x is less than or equal to a and y is less than or equal to b. So this is the definition of cumulative distribution function or joint CDF of two-dimensional random variable. So it is simply generalization of this definition. Instead of one variable, here we have two variables. So here we consider probability that capital X is less than or equal to A and capital Y is less than or equal to B. So first definition is joint cumulative distribution function. So let x and y be two discrete random variables. The joint CDF of x and y is denoted by capital F of AB and is defined as f of AB equal to probability of the event x is less than or equal to A intersection y is less than or equal to B. Here A and B can take any real values. Now we can obtain the distribution function of individual random variable from the joint distribution function of x and y in this way. Suppose we are interested in the CDF of random variable capital X, then by definition f of a equal to probability that capital X is less than or equal to a. So in the joint CDF we fix this event x is less than or equal to a and we vary y. So probability that x is less than or equal to a comma y is less than infinity. Now this y less than infinity can be written as limit of we can write y less than infinity as limit of this event as b tending to infinity. So I have written in this way, limit b tending to infinity x is less than or equal to a, y is less than or equal to b. Because this is independent of b, so limit of x less than or equal to a as b tends to infinity is x is less than or equal to a. Now this is nothing but we can assume that probability function is continuous, so we can interchange limit and this function. So probability of limit equal to limit of probability of x is less than or equal to a, y is less than or equal to b. Now this is nothing but value of CDF at point AB. So limit of f of AB as b tending to infinity, and this equivalently we can write as f of a comma infinity. So we can obtain CDF of individual random variable from the joint CDF in this way. Suppose we are interested in the CDF of y, then we can write that this is going to be here we vary this small a, b is fixed here, so this we can rewrite as limit a tending to infinity f of ab, or equivalently CDF at infinity comma b. So similarly the CDF of y is given by fb equal to probability that y is less than or equal to b, and this is expressed as limit of joint CDF at a tending to infinity, which is equivalent to f of infinity comma b. These are some remarks. The CDF of x and y, if we consider individual CDFs of random variables x and y, then they are sometimes known as marginal distributions of x and y, or marginal CDF of x and y. So these two are this f suffix x of a and this f suffix y of b are nothing but marginal distributions functions or marginal CDF of x and y, which we can obtain from joint CDF in this way. Now this is another remark: all joint probability statements about x and y can be answered in terms of their joint distribution function or joint CDF. So for example, if we have this probability that x is greater than a and y is greater than b, so this probability can be answered using joint distribution function of two random variables x and y. So we can understand this, how to convert this in terms of joint CDF. So we know that if we consider this event, x is greater than a and y is greater than b, then this is intersection of two events, x greater than a and y greater than b. So probability of this event will be equal to 1 minus probability of complement of this event. So this I have written as 1 minus probability of complement of x greater than a and y greater than b. Now we know that this comma indicates and, so this is nothing but intersection of two events. So I have 1 minus probability of complement of x greater than a and y greater than b. Now we know that if we take complement of intersection, then this is equal to union of complements of these two events by De Morgan's law. We know that probability of a intersection b complement equal to, or we simply need this complement of a intersection b will be equal to a complement union b complement. So that we are using here. Here event a is x is greater than a, event b is y greater than b. So this is equal to complement of x greater than a union complement of y greater than b. Now complement of x greater than a is the event that x is less than or equal to a. So this we will replace by capital X less than or equal to a, and this we will replace by capital Y less than or equal to b. So this is nothing but 1 minus probability that x is less than or equal to a union y is less than or equal to b. So we have probability of union of two events, and by addition rule this is equal to probability of a plus probability of b minus probability of intersection of a and b. So we use this formula here and we obtain that this probability of union equal to probability of first event plus probability of second event minus probability of intersection of two events. Now this first event probability that x is less than or equal to a is nothing but CDF of random variable x. Similarly this is nothing but CDF of random variable y at point b, and this is nothing but joint CDF of x and y at point AB. So we replace all these things by cumulative distribution function values, and if we take negative sign inside the bracket we obtain this. So this probability is expressed in terms of CDF of random variables x and y, and also in terms of marginal distribution functions of x and y. So sometimes they can ask you this type of questions, prove that this probability equal to this one. So you must be able to answer that, how to express probability statement in terms of joint CDF. This is another remark. You can prove this as a self exercise. If we consider probability that capital X lies between A1 and A2 and capital Y lies between B1 and B2, then this is equal to value of joint CDF at endpoints plus value of joint CDF at first endpoints minus, here we are taking in reverse. If we consider first point here, we consider last point from here A1 B2, and if we consider A2, then we consider B1. So A2 B1, A1 B2 and A2 B1. Here we have positive sign, here we have negative sign, and here we assume that this A1 is less than A2 and B1 is less than B2. Now after this, the next definition is conditional probability mass function. So to define conditional probability mass function, we can recall the definition of conditional probability. We know that if A and B are two events, and if probability of B is positive, then probability of event A given that B has occurred is given by probability of intersection of A and B divided by probability of B. So using this definition, we can define the conditional probability mass function. Suppose we are interested in the probability of the event that x equal to x given that y is equal to y. So this is equal to, here we consider capital A equal to this event, capital X equal to small x, capital B equal to y equal to small y. So this is equal to probability of the intersection of these two events, x equal to x, y equal to y, divided by probability that y equal to small y. This is nothing but, this we can write in this way, probability that x equal to small x, y equal to small y, divided by, this is nothing but value of marginal probability mass function of random variable y. Now if this value is positive, then this is valid. Now if we consider probability that x equal to small x, y equal to small y, this one, then this is nothing but value of joint probability mass function of two-dimensional random variable xy at point xy divided by value of marginal probability mass function of random variable y. So we obtain that probability of the event x equal to x given that y equal to y is equal to division of joint probability mass function at point xy and marginal probability mass function of random variable y at point y, provided this value is positive. So this is known as conditional probability mass function of the event x equal to x given that y equal to y is occurred. So it is denoted by P of x is, we have to find out probability of x equal to x given that y has occurred. So we write x in the numerator, y in the denominator. So this is the notation for joint conditional probability mass function of two-dimensional random variable, and here in the bracket we write x by y. So this is the conditional probability mass function of random variable x given that random variable y takes the value small y. Now if we are interested in the conditional probability that y equal to small y given that x equal to small x, then here we will interchange the role of x and y. So in this way we can remember the definitions of conditional probability mass functions. So let x and y be two discrete random variables with joint probability mass function denoted by p of xy suffix xy. The conditional probability mass function of random variable y given that x equal to x is defined in this way. So we are considering conditional probability mass function of y given that x equal to x. So here we use in the suffix we write y divided by x, and here in this bracket we write y by x. So this is equal to joint PMF at point xy divided by this is marginal probability mass function of random variable x, or PMF of random variable x at point x, and this is valid for all values of x for which this PMF has positive value. Now similarly we can write the definition for conditional probability mass function of x given that y equal to y is defined as p of x by y suffix x by y equal to value of joint PMF at order pair xy divided by value of probability mass function of y at point y, and this is valid for all y for which PMF of y is positive. So if we have given this event y equal to y, we will divide by probability mass function of random variable y, and if we have y given x, we will divide by PMF of random variable x. In the numerator we will always have joint probability mass function of two random variables. So you don't have to cram these definitions, this is simply generalization, or this you can remember by the definition of conditional probability. We are just using this definition as I explained here. So we will remember this conditional probability mass functions, and if you are writing this type of probabilities in the table, whatever distribution we obtain is known as conditional probability distribution. So we consider one example related to the conditional probability mass function. Suppose that pxy is joint probability mass function of x and y given by p of 0 0 equal to 0.4, p of 0 1 is 0.2, p of 1 0 is 0.1, and p of 1 1 is 0.3. So we have given the values of joint probability mass function of two random variables x and y. So from this we can see that possible values of x and y are x can take values 0 and 1, and similarly y can take values 0 and 1. So possible values of random variable x and y are 0 and 1. We have to calculate the conditional probability mass function of x given that y equal to 1. So we use the definition. The conditional probability mass function of x given that y equal to 1 is p of, in the suffix we write x given y because we are here asked to find out probability mass function of x given that y equal to 1. And here instead of x by y we write x by small 1 because value of small y is 1. This is equal to value of joint PMF at order pair xy divided by value of probability mass function of random variable y at point y equal to 1. So here we write 1. So we are using this definition. We are using this definition for all values of y such that this is the. So we are using this definition for y equal to 1 because we are asked to find the probability of x equal to x given that y equal to 1. So this we are using for particular value of y, which is 1. So here we will consider y equal to 1. So this is by definition p of x by 1 equal to joint PMF of xy divided by p of 1, and this we have to find for x equal to 0 and x equal to 1. So for that we will require value of marginal PMF of y at point 1. Now if you remember, if we are interested in the marginal PMF of individual random variable, then we consider summation over all possible values of joint PMF, and summation is over all possible values of x, because y is fixed here. Here fixed value of y is 1. So if we consider y equal to 1, we have this definition: p of 1 equal to summation p of x1. We are using this definition for y equal to 1, and we have to consider summation over all possible values of x. Here possible values of x are 0 and 1. So sigma p x1, x is from 0 to 1. So this is equal to, if we take x equal to 0, we have p01, and if we take x equal to 1, we have p11, and we are given the values of this probability mass function. p01 is 0.2, p11 is 0.3. So using these values we obtain p of 1 equal to 0.5. So we obtain this conditional probability mass function. If we take this value p by 1, we put here, and we obtain that p of x by 1 equal to pxy over 0.5, x equal to 0 and 1. Now first we put x equal to 0, and of course I have to replace this y by 1, because I am interested for y equal to 1 only. So now I calculate conditional probability mass function at x equal to 0 and x equal to 1. So if I put x equal to 0 here, I have p of 0 by 1 equal to p01 divided by 0.5. p01 is 0.2 here, so I obtain 0.2 divided by 0.5, which is 2 by 5. Similarly, I obtain conditional probability mass function of 1 by 1, so I have to put x equal to 1 here. So we have p11 divided by 0.5. p11 is given as 0.3, so I obtain 3 by 5. So I have conditional probability mass function of x given that y equal to 1 is p of x by 1 equal to, for x equal to 0 it is 2 by 5, for x equal to 1 it is 3 by 5, and we can write that it is 0 otherwise. So in this way we can find out conditional probability mass function of one random variable given that another random variable takes some value. So in this way we can write the conditional probability distributions. Now next definition is independent random variables. So this is also can be generalized from the definition of independent events. We know that if two events are independent, or two events are independent if probability of their intersection will be equal to product of their probabilities. If probability of A intersection B equal to probability of A times probability of B, then A and B are independent events. So this we can generalize, or using this definition of independent events we can define the independent random variables. So suppose I have two random variables x and y which are discrete, then we know that if I consider p of xy, that is joint PMF at point xy, then this is equal to probability that x equal to small x and y equal to small y. So this is nothing but probability of intersection of these two events. So these two events are independent if this probability of intersection will be equal to product of probability of x equal to x into y equal to y. Using this definition, two events are independent if probability of their intersection equal to product of individual probabilities. So here we have x equal to x intersection y equal to y. So these two events are independent if this probability equal to probability of x equal to x into y equal to y. Now this is nothing but value of probability mass function of x at point x, and this is PMF of y at point y. So two discrete random variables x and y are independent if P of xy or if joint PMF at order pair xy will be equal to probability mass function of x at point x into probability mass function of y at point y. So in this way we can define independent random variables. So suppose I have two discrete random variables x and y. If any one of the following properties is true, then others are also true and x and y are independent. So this is first definition. If P of xy equal to px into py for all x and y, then x and y are independent. Now what are the other definitions for independent variables? So another definition is, suppose we are interested in the conditional probability mass function. So this conditional probability mass function we can understand here. Suppose I consider conditional probability mass function of x given y, then by definition this is equal to P of xy divided by py. Now if x and y are independent, this is going to be px into py, as I just explained that two variables are independent if pxy equal to px into py divided by py. Now this is positive when we are defining this, so this will cancel out. So if conditional probability of x given y equal to P of x, then also x and y are independent. So there are several definitions for the same concept of independent random variables. You can write any one definition. So I have written these 5 properties which are several different definitions for the independent random variables. So first one is x and y are independent if this property is satisfied. P of xy equal to px into py. Second one is conditional probability of y given x equal to probability mass function of y for all x and y with this probability is positive. Similarly, if we consider probability mass function of x given y, then this conditional probability will be equal to probability mass function of random variable x, such that this is satisfied. Now if we consider this probability of the event that x is in set A, y is in set B, this is equal to probability of x belongs to A times probability of y belongs to B for any sets A and B in the range of x and y respectively. So if this property is satisfied, then also x and y are independent. And last property is in terms of joint CDF. If joint CDF at point AB equal to CDF of x at point AB into CDF of y at point AB for all A and B, then also x and y are independent. So these properties are equivalent. If one is satisfied, 1 implies 2, 2 implies 1, and if in similar way, if one property is satisfied, then others are also true, and if any one property is satisfied, then x and y are independent because all properties are equivalent. So we will remember these definitions of conditional probability mass functions, independent random variables, and joint CDF of x and y. And with this I conclude here. In the next lecture we will discuss some examples related to all these concepts. So this is all about this session. I hope you like it. Thank you very much.